Hello everyone. I would like to take this opportunity to welcome today to our webinar. Today we'll be taking a look through our U.S. Bellows subdivision of some fabric expansion joint applications. Our webinar today is being presented by Piping Technology and Products. My name is Jerry Godina and I will be your host for the webinar today. If at any time during the webinar you have a question, please feel free to chat it to us in the text box you see to the right. Or if you prefer, you can hold your questions until the end, where we'll have a brief question and answer session. I would like to point out that we do have panelists standing by during the webinar. So once again, if something does strike you as we're proceeding, please don't hesitate to ask that question, and hopefully we can provide an answer as we progress through the webinar. Also, I'd like to remind all of our Texas PEs out there in attendance today that you should be receiving your certificate for 1 PDH credit hour within the next couple of days. If you don't see that in your inbox, please drop us a line at info@pipingtech.com and we'll be sure to get that out to you. So once again, I want to welcome everybody for joining us, and we'll go ahead and get started. For those of you who may not be too familiar with this, I'll let you know that we are U.S. Bellows. We're a subdivision of Piping Technology and Products. We're a manufacturer of all types of expansion joint components. We'll be talking specifically today about fabric expansion joint applications, but in terms of design capability, manufacturing capability, the U.S. Bellows division can develop designs using other materials, any type of metallic expansion joint components which might be needed to accommodate different design considerations, temperature application-wise, media application-wise, deflection application-wise, all those types of things that would come into effect when designing, fabricating, and ultimately utilizing an expansion joint assembly. We're located here in the Houston, Texas area, so it does give me an opportunity to either invite any of our audience members who are here on a regular basis, or if you're ever in our vicinity and want to see some of the things perhaps that we're talking about in particular today, or any of the other capabilities that we might hint about in terms of our expansion joint design, or any of the other assembly components that are developed through our parent, Piping Technology and Products, please don't hesitate to contact us. We have more than a few folks who'd love to show around, get to know you, and have a little bit more interaction than we might have on a normal basis. In terms of our U.S. Bellows team, just to show you, give you an idea of who they are, these are our managers. John and Muse up on the top there. You see some of our engineering group, some of our production personnel. Just to let you know, we're extremely proud of the work they do, the job they can accomplish, and so if you ever need to put a name to a face, well, or sorry, a face to a name, here you go. You know, might be dealing with a lot more of a email or something like that on a telephone call, but like I say, if you ever want to put a face to the name, here you go, and you may become more familiar with some of these folks than others. And as I mentioned, just by way of introduction, we're the U.S. Bellows subdivision is a member of our Piping Technology and Products family. Just in case you don't know everything that we do, Piping Technology and Products basically is the parent company developing and designing all types of pipe support elements, anything that goes into supporting our piping mechanism. And the U.S. Bellows subdivision, it deals exclusively with those expansion joint assemblies, but other things included in that family of products include our Pipe Shields division, which handles insulated support elements, our Fronic subdivision, Fronic Anchor Darling, which develops snubber components, our Sweco subdivision, which handles ASME components, such things like a pressure vessel, launcher, receiver, or something along those lines, and the PTFE parent, if you will, the founder of the entire corporation, develops those pipe support elements, spring supports, variables, constants, pipe attachment elements, be they a clamp or a saddle or something along those lines. And in totality, we're more than 450,000 square feet of shop space here in the Houston, Texas area on a 40-acre contiguous property located near the ship channel. And so the U.S. Bellows subdivision was essentially established early in the 1960s, and they joined the PT&P family directly in 1995, and they've been here ever since. They've been helping and also in acquiring different elements or different facets of other expansion joint manufacturers, including the U.S. Bellows subdivision of RM engineered products and high quantity of Lord's manufacturing equipment also acquired in 2011. So it's an expanding element within the piping technology and products overall family. One of the things that we're especially proud of, in essence, is our inclusion in EJMA, or the Expansion Joint Manufacturers Association. We have folks on both the technical committees, and they meet, are part of the research, the development, the design aspects, helping to establish those standards so that the expansion joint industry as a whole can be unified, can have some standardization, can perform and function no matter the specific manufacturer. Obviously we'd like to be that, but in general you also want to have an impact on the overall industry, ensuring that the design, the manufacture, the production, the utilization of expansion joints follows that uniformity, follows that standardization, and can be adapted to the industry requirements, can be up to date in terms of new applications, new materials, and new design strategies and such. And so we're extremely happy to be part of EJMA. We've got 10 years now on both the technical committee side and the management committee side as well. Okay. And also, just to let everyone know, our U.S. Bellows subdivision has the U.S. or the ASME U stamp, our stamp as well. We're currently a minority business enterprise, ISO 9001 certified. Actually, we've just gone through our 9001 2015 certification, and we do have the approval, and we should be receiving our recertification or certification of the new standard, I should say, in a couple of weeks or so. So that's already been established as well. Okay. So as we continue, that's the introduction of who we are, U.S. Bellows. I'd like to welcome all of our new audience members who may be just joining us. Today, we'll take a look at one particular aspect or facet in the overall expansion joint family, and that's to take a look at fabric expansion joints, how they might differ and how they also might be the same in comparison to what might be considered the standard or the metallic expansion joint components. So we'll take a look at basically an overview, looking at some of the basic ideas, concept involved in fabric expansion joints, paying a little bit of attention to those specific belting materials that make up the heart of the expansion joint, and then looking at those different components, different assembly construction, different applications where we'd use some fabric expansion joints, and then briefly going over some of the points to remember during the installation phase of a fabric expansion joint, maybe some of the things to look at if you're having an in-service inspection to review during the life cycle, in particular of fabric expansion joints versus other styles and devices that may be in use already. Okay, so when we look at the big picture, the overview of expansion joints in general and fabric expansion joints in particular, there are a couple of things that we want to keep in mind. The functionality of the fabric expansion joint is essentially the same as you would find in a metallic expansion joint. It's to compensate for either thermal growth deflection between fixed entity and some moving portion of our, in many cases, a ductwork assembly, or in some cases to compensate for misalignment or deflection as a consequence of the operating cycle of our system. The difference is, or one of the differences, that we can absorb, relatively speaking, larger deflections than could be accommodated in the same span or the same space available than you might find in a metallic expansion joint. That's one of the benefits of utilizing the fabric material in the expansion joint assembly. There are a variety of applications where they're used, mostly in high temperature media combinations of low pressure, such things you might find as an inflowing air or an outflowing gas in a large combustion process. That's somewhat, if you want to consider the typical application for a fabric style expansion joint assembly, wherein we can utilize an element, that fabric element, which in general can lead to higher levels of displacement or deflection, sometimes also not in just the axial direction, so to speak, but sometimes in that lateral deflection as well, much higher deflections than can be accommodated by a metallic expansion joint or metallic bellows section within that same amount of space allotted between our infrastructure and our moving component. Now, where we might find expansion joints in a variety of applications. In fossil-fired power plants, paper plants, cement plants, refineries, chemical plants, any place that we can utilize their capabilities, anywhere that we can, or a necessity requires that we produce that higher deflection than normal in a confined space or a much more limited space, and where we're dealing with the same design requirements that we might find. And we'll note that the fabric belt simply takes the belting component in that expansion joint assembly, simply takes the place of where we might consider the standard metallic bellows element. It does the same functionality. It deforms to permit that, if we talk about primarily thermally induced deflection, to occur without increasing the stress on our duct system or our piping system, or without increasing the stress levels that would be seen on our supporting infrastructure. And the belt then, though, what becomes important or critical to review, that it can withstand all those thermal requirements. Look at the pressure. Even though we're primarily dealing with low pressure applications, there are still limitations in terms of the design, what is low, what is medium. You know, those ranges have to be known as well. Any type of chemical reactiveness, what is that media that's going to be flowing through that expansion joint component? Do we have to resist any flutter applications that might be seen, or differences in that pressure that would be seen during our operating cycle? What is the temperature level that will be attained during the operating cycle of that component? Are there heavy particulates within that media that will eventually degrade? Are bellows exposed to those particulates? Do we have to make compensation by adding extra elements within that bellow to protect it during its life cycle? What is the exact media that would be flowing through that bellows component? So all of those different considerations also have to be incorporated in that design and ultimate utilization of a fabric expansion joint. And so as we continue, what we'll talk about and expound a little bit are on some of the different terms, phrases that we'll be seeing. The first we've kind of mentioned a little bit of that fabric belt. That's essentially the heart, the main component to be dealt with. And the other elements of that design and that overall configuration will then flow as a result of our particular application. How are we attaching that component to both our ductwork or our piping system and the flange itself. Oh, I'm sorry, the flange to the belt material. Is there a necessity for any type of insulation material, an accumulation barrier? What types of fasteners will be used precisely? Are there any backup bars? Are there any limit rods? Anything else incorporated into that overall design? And we'll start to take a look at some of these, hopefully starting with a little bit basic designs or elements that go into the design of a fabric expansion joint, and then look at those additional components which can be incorporated into their overall functionality. Okay. As we're starting to take a look at the basic elements, the basic overview, we want to keep in mind those factors which would influence our expansion joint design. The design conditions, as we talked about, what is our operating temperature? Is there a standard operating temperature and a maximum design temperature that we have to consider? What is that deflection or movement cycle? Is it both a compression, extension mode during our operating cycle from our initial set point? Is there, again, a maximum overload condition that may have to be taken into account during our operating cycle? What type of media will be flowing through that expansion joint? Are there any, or what are the types of things that we want to look at, include whether or not that's a wet or a dry media, whether there are any corrosive elements to consider, whether it's an abrasive element, whether particulates will be flowing in that media as well. What is the design pressure that would be seen? Is there any consideration for flutter of that component which must be incorporated? Are there changes in that pressure design which may occur at any point in our operating cycle? What will be the attachment method? We'll look at and see that you'll have basically two primary methodologies of attaching that fabric expansion joint in position. One being a weld-in style of attachment, another being the bolt-in style of attachment. There are pluses and minuses to using it either one. One may have more adaptability in terms of any anomalies or discrepancies that we might find when we actually try to put that unit in position, and another might be more of a easier in terms of its overall installation process. And so it may be a trade-off, one or the other. It may be a mandate of a particular facility, whether or not they can be welded in or bolted in. It may mean more in terms of the installation as in terms of why one particular methodology is chosen versus the other. And so as we go through, you might see that that expansion joint can be simple in design, or it can become more complicated in design when we do take into consideration all those design aspects. They'll have an influence on whether or not, for example, a liner, or talk about insulation, will be incorporated, whether there'll need to be an accumulation barrier, whether special gasketing material will be incorporated into that design. All of those things will be incorporated and included whenever necessary. You can run the gamut in terms of fabric expansion joint design utilization from very simple to very complex, just as you might see in a metallic expansion joint design. Some have very small deflection cycles they have to go through. There's no considerations for other than small lateral deflection. We wouldn't have to worry about any torsional deflection or any lateral deflection that would be seen. It's all in one direction. And so that may lend itself to a rather straightforward, simple design, or you can then increase and expand upon that level of complexity to incorporate a large amount of components, considerations, operating cycle conditions that will have to be incorporated in that total design. And we'll start to take a look at some of those as we continue. And so that just may mean, as I talked about, that your level of complexity for the overall expansion joint assembly increases depending upon what are the total design considerations that have to be incorporated. Okay, and we'll take a look at those as we continue on, but just keep that in mind as you're even in the development phase of deciding whether or not a fabric expansion joint is applicable or not. It takes a lot of consideration in terms of our design considerations, in terms of all of those key elements which must be incorporated whenever required. So as we start looking at some of the details, what we want to take a look at first are the belts themselves. The belt essentially will be the heart of that expansion joint component. The belt will be what accommodates that deflection. The belt will be what determines our temperature range application. We'll find that that determines our deflection availability, the number of cycles over which that expansion joint can be utilized. All those, maybe even the type of attachment which is most applicable, will go into a review of that fabric belt itself. So that's why it becomes primarily the most critical element to review and to establish in terms of that fabric expansion joint design. A number of materials can be utilized. There are two basic families which we'll talk about in terms of the fabric expansion joints. That would be the fluoroplastics, sometimes known commercially as Teflon. The chemical resistance of this material is what lends it, the high chemical resistance, I should say, what lends it to more applications in fabric expansion joints. And then you have fluoroelastomers, or sometimes referred to as rubber expansion joints, or rubber material. You might know them, again, via their commercial names, Viton, Hypalon, things of that nature. So you've got fluoroplastics, which are utilized in the fabric belt material, or fluoroelastomers as well. Okay, and some of the things that we want to keep in consideration, again, are the different variables to look at are that material strength. Essentially, as we talked about, we're trying to utilize a fabric material in the same manner that we would utilize a metallic material in a bellows configuration. So we're looking at the tensile strength of that component, the ability of that element in terms of its chemical barrier properties. Can it withstand the atmosphere to which it will be exposed? Is there the necessary requirements to add any insulation material to that overall system so that our expansion joint doesn't become a heat sink at a particular location of our operating cycle? Is there any type of application where we might increase the strength by utilizing some cross-film technology, by adding multiple layers, by bonding those layers to other belting materials to increase any of those strength characteristics that we might need, resistivity to chemicals and other abrasive materials that we might need? And so it becomes a strategy in terms of review of that material as well. And so as we look at some of those different components, we'll look at this material comparison chart and kind of give us an overview again of what we're talking about in terms of, you know, everything is relative. So low temperature to one person might be a high temperature to another. So when we're looking at, for example, the different components that are used in fabric expansion joints, we'll talk about them, see some of their characteristic design strategies. So if we're looking at keeping our temperature range as one of the overriding or guiding characteristics, we'll start with ambient to about 250 degrees Fahrenheit. You see a lot of times what's utilized in there. We talk about the butyl rubber elements, neoprene, Viton. The advantage is they have a high tensile strength. They are highly resistant to weathering and ozone considerations. The pressure range is the medium. They can be used there. The chemical resistance is relatively high. And so you would use those where applicable. As your temperature increases, we might be looking at something like a fiberglass reinforced silicone material, more resistant to deterioration by weathering different types of components as the temperatures increase, 500 to 700 degree range, for example. You've got some PTFE impregnated fiberglass components, some PTFE coated glass components. They have high tear, increased resistance. They also, because they're using that PTFE component, we refer to that, as we talked about before, mostly as Teflon, you'll see some low friction capacity in there so that you can hopefully maintain the flow characteristics of your media by introducing those PTFE elements within that fabric expansion joint. Now, when our temperature ranges increase a little more, we're using something like a silica fabric cloth for those high temperature applications. You have a high abrasion resistance. Now, the pressure ranges start to decrease. So as we talked about, in many regards, for everything that's gained in one application, you might lose a little bit. So when our temperature range is, for us, the high category, 1,000 degrees upwards, about 1,800 degrees, you may have that silica and PTFE fabric cloth, but now included within that system some insulating material. For example, KO wool style is perhaps the standard. So you have a high temperature stability for that overall system, and you can produce some excellent resistance to those chemical components to which they may be exposed. And so you might find those applications for that higher temperature, furnace application, for instance, a kiln where you have those temperatures which exceed 1,000 degrees Fahrenheit. And so you're going to develop an overall belt system, if you want to think of it that way, which incorporates some insulating materials as well. And so as we continue, we just take a look at some of those close up. If you are looking at the PTFE coated glass cloth, we talked about the upper temperature range, about 600 degrees Fahrenheit. The tensile strength, which is utilized here just for your edification in terms of what the capacity or capabilities of that element would be. As we talked about, it's used in a lot of applications where we have to have a high chemical resistance during its life cycle. The reinforced silicone fabric, as we talked about, a little higher temperature range, up around 700 to 1,000 degrees Fahrenheit, a tensile strength about 1,300 psi. You can use this, as we talked about, as an excellent gasketing material. It has some extreme, well, not extreme, but in the higher, lower temperature resistance. It's a non-toxic. It's chemically inert. You can use it in those applications as well. An aluminized glass cloth, tensile strength a little lower than we've seen before, but it resists most acids and alkalis and things like that when we're exposing that fabric expansion joint to those perhaps harsher operating conditions, chemically speaking, or media-wise in terms of their application. You may, again, as we talk about, have a lower tensile strength than we see in other fabric materials, but they're more resistant, more applicable in those acidic environments, those alkali environments, and things of that nature as well. The silica oxide glass cloth, as we talked about, is our high temperature application. You find them in various widths, thicknesses. They maintain their tensile strength even at those high temperatures. You won't find a degradation that you might see in some of the other components. You might find that the temperature range or the temperature application becomes critical because of the fact that some of those other materials may also have a decreasing strength characteristic as they're exposed to higher and higher temperatures. Now, with the silica oxide glass, one of the things that's most beneficial is that it can basically maintain those strength characteristics at those different temperature ranges. When we're, say, at ambient temperature, if we're talking about a cycling system that goes from ambient to its temperature and continuously back and forth, so that you can maintain those tensile strength characteristics, can utilize that component at the high temperature phase or the low temperature in terms of ambient temperature phase, and have it work effectively at both instances or any point in between during our operating cycle. The PFA fluoropolymer film, it can be either clear or translucent. This one is used because it has an outstanding flex life and is highly resistant to any stress cracks. You can, and a lot of times, incorporate these where you have a high degree of cycles that must be undergone, and it has excellent electrical properties and weathering ability as well. Okay. Now, the elastomer belts, what we call the rubber belts, are essentially built up or built of multi-layers of sheet reinforced, a lot of times with fiberglass or an aramid fabric. And the majority of cases, what you're starting with is an 1/8 of an inch single layer component. It can be built up as requirements or as safeguards the entire design. It's used primarily as a flat belt, or it can be integrally flanged in a U-shaped cross-section that bolts directly to the duct or the equipment. And again, they're used because they inherently have a high degree of flexibility. They can be built with reinforcement components which increase their abrasion resistance, and they are very flutter resistant, meaning you can have a long service life when we're not exceeding those design characteristics. They have the capacity to, in many instances, resist or highly resist those abrasive components that might be seen within that media flowing through. Here's just an application. You see the single belt component, 1/8 inch thick with a reinforcement. You can build different or the quantity of layers or levels of that elastomer in order to build up the strength characteristics, the abrasive resistance characteristics as well. Okay. And so what we've seen thus far is that belt is the heart of the fabric expansion, or that belting material. Now let's start to talk about applying those components in different methodologies, in different utilizations throughout how they'll be attached to the elements, what goes into that design as well. Okay. Again, where we might use fabric expansion joints, we'll take a look at different areas, different applications. Here we're just using a fossil fuel fired power plant to illustrate some of those places where it might come into utilization. You've got the boiler, you've got an economizer, you've got different junctions between those elements. You might put it in any of those ductwork components to allow for those, as we talked about, primarily thermal deflection cycles to occur and things of that nature. And so as we continue, what we'll take a look at maybe are some more specific examples. I'll give you an idea of how they can be utilized in totality. And one of the first ones that we'll look at in terms of their complexity, or I should say maybe lack of complexity, are what we term a simple furnace bag application. Again, you'll note that there are very straightforward application for what we call the furnace bag. It basically consists of multiple layers of a flexible, flame and heat resistant component. They're primarily nickel reinforced that helps to reduce the airborne fiber and increase the tensile strength. But if you'll notice, what's done is that there's very straightforward application in that you're utilizing the furnace bag application primarily in a particular system wherein we're trying to make a transition from a stationary portion of the furnace to a moving component, usually moving within that furnace position, and in many instances going through a relatively drastic change in its profile, meaning from a large diameter to a small diameter. From a rectangular section to a round section. And as we talked about in the beginning, one of the major benefits that you find in the fabric expansion joint elements are that you can make those transitions maybe pretty drastic transitions in terms of the profile of that belting material in a relatively short space. If we take a look primarily at the lower photo, you see that you have a large diameter inlet and a very small diameter outlet, relatively speaking, over the length of that fabric expansion joint component. And as we talked about or alluded to previously, if we try to do that or configure that element out of a metallic bellows component, it might be very difficult to make that drastic transition from one to the other in a metallic style of component. But by utilizing the higher degree of flexibility in the fabric expansion joints, you can make those relatively drastic changes in configuration and still allow that component to absorb the deflection that it would see during its operating cycle. And as we see one more application in the next slide, you'll see again a different geometry is our kind of one of the guiding influences of that design. It's still a relatively straightforward application. You have the simple bellows unit attached via only clamp elements. There are no flanges, there's no welding involved, but what became one of the overriding considerations in this style of, even in the relatively simple construction design, was that we were developing that fabric expansion joint to accommodate, again, that drastic transition from a rectangular or almost oval shaped inlet to the round or pipe outlet, and that it was not centered within that component, so that you had an offset between the starting point or the initial point of our pipe within that furnace floor, and that we had to accommodate also some lateral deflection during the operating cycle. Not only vertical or axial deflection of that piping system, but lateral deflection as well. And so the fabric expansion joint component lent itself more readily to this application due to its ability to make, again, that transition and to accommodate those relatively large deflections during its operating cycle within that short span. There's not a lot of space between that furnace floor and where we had to attach, or one has to attach, that lower portion of the expansion joint. And so, and also incorporated into this design, because there are some elements which you can't build because you're relying upon that strength, you know that there was also a steel coil which was incorporated into that design to help during those lateral deflections as well maintain the overall shape of that bellows section, the fabric portion of that belt. Okay, all right. But these that we've looked at are essentially what you might consider the most basic or the most straightforward in design. Most expansion joint elements have a higher degree of complexity in them. And so when we're looking at that, there are a few things that we want to keep in mind that will also have an impact that we talked about. You know, the things that we always want to review, or the things that we talked about, are our pressure, our temperature, the media running through there. But we also have to consider, in probably the majority of other cases, what type of end condition are we dealing with? How much movements and what's the life cycle that we have to incorporate into that design. So all of these inputs will be utilized when developing a fabric expansion joint. They are probably not going to be as straightforward as we saw in the furnace applications, or the furnace bag application, I should say. And so when we take those design considerations as a whole, what we'll find then is the overall design, then looking at what are our end connections. What is our pressure range, temperature range, the media flowing through it? How much movement do we have to accommodate? Where is that movement occurring? Simply in the axial direction. what then materials do we have to utilize, what will be the dimensions, what's our spring rate generated, are there any ancillary components that will be incorporated in that design. So let's take a look at those as we continue on. Here we'll take another example, an economizer to an air heater example, and might find that yes, there are flange connections which are being utilized to attach that expansion joint together. You might find other applications where you've got, for example, a high temperature, we'll call dirty flue gas element. And so you're considering both the temperature range that you have to look at. You have to look at that flue gas that's flowing through that component and then incorporating different design elements within there. The first one that we want to look at or discuss are the connection points of our expansion joint with our ductwork or with our piping system or whatever we're attaching it to. Now, one of the main things that we want to consider is whether that's going to be, as we alluded to a little bit earlier, a bolted or a welded design. And that, in many instances, is a matter of installation, is a matter of what our capacity is at site, and you'll see that the configuration can remain the same 90% between one expansion joint and another. It just may be influenced by whether or not it's going to be a welded design, as we see in the middle configuration, or if we'll have to incorporate bolted design components, as we see on the right-hand side and the left-hand side. There are, as we talked about, trade-offs one for the other. Welded designs sometimes, as we talked about, can be more flexible in terms of their field fit-up construction. In terms of a flange design and a bolted construction, those two attachment points are going to have to be precisely where we anticipated them being. If you do a welded design, you may have the opportunity to build a little bit extra in that expansion joint and fit it as we need to the exact position of our ductwork, as we talked about, that we find and the actual field conditions or the site conditions might mandate. And so that's maybe one consideration to take in mind. Now, maybe we don't have the capacity to do any welding out in the field. And so that would mean, though, that the recourse is to utilize a bolted configuration or a bolted construction for that expansion joint component. But that's one of the main considerations that goes into the overall design as well, whether it will be welded in, whether it will be bolted in as well, or in. And then here we can then look at some overall designs, looking at them schematically. Again, relatively straightforward. No inclusion of baffles or any other components. The only thing that we're primarily concerned with are the attachment and the bellows attachment to our ductwork and the attachment of our bellows to its own flanges. And so you can see welded designs, upper left hand, middle there, and the far right, all of those welded configurations. You can see them mimic essentially the same overall designs in welded versus bolted in. You see that the expansion joint component, the fabric belt, its tie rod, tie attachment points can be the same. The only thing that was different was between the welded design and the bolted design below. Okay. Now then, as we start to look at other design considerations, other applications, we're going to look at how we may need to introduce baffles, which are incorporated into the overall design. And you'll see that the most critical characteristic of those baffle inclusion are that they are in the flow direction, that we don't essentially install that expansion joint in the opposite direction. So the baffle consideration goes in line with the flow of our media through that component. but you see the same design characteristics can be applied again. We've now gone from bolted, welded. That becomes one design consideration. The inclusion of baffles in the overall design, that becomes another design consideration, and ultimately production consideration. Then do we have to incorporate now not only baffles, but maybe that insulation pillow to isolate our fabric expansion joint from the high temperature media? Do you have to put a seal in between that baffle and the attachment point so that we won't have exposure to an abrasive media, something along those lines? So now you can increase the level, increase the components included in that overall design. You're looking at now a combination of those design considerations to produce the overall configuration of that fabric expansion joint. You may have the necessity to incorporate all of those different components: the baffle, the insulation pillow, the seal, which isolates both the insulation and the fabric belt from our media. And so all those different components may have to be included. How are we welding that in place, or can we bolt it in place? So those bolt flange dimensions known. You know, all of those different design considerations have an impact on the final assembly and the final construct of that expansion joint. So let's just take a look now at some of those specific or particular applications. Here you see a ductwork application, 60-inch in diameter. See that you have the bolted connection of the belting material to the flanges, but that the flange themselves are welded in position at the ductwork components. Okay, this for a sulfuric acid plant, again taking into consideration that corrosive atmosphere. Okay, here you see some others, again welded construction in terms of the framework of the expansion joint and bolting that fabric bellows in position. This happened to be a 78-inch fabric expansion duct joint used on a 90-degree elbow. Okay, as we talked about, we're dealing with what we might consider relatively low pressure conditions, 5 psi gauge, but high temperature, relatively speaking, 750 degrees Fahrenheit. But you could accommodate, as we talked about in this relatively short span, about 2.5 inches of lateral deflection, meaning we're going to have a cold preset offset in that system, and also 2 inches of axial compression. That combination would be very difficult, probably impossible, to incorporate via a metallic bellows within that same space allotted between flange to flange connection. And so you're going to incorporate both lateral deflection, axial compression. You're going to have an offset during the installation of that component, which all can be more readily incorporated via a fabric expansion joint than we could probably incorporate with a metallic expansion joint bellows section. Okay, as we continue, looking at some neoprene rubber ones, same kind of applications here, though you have a bolted flange connection in the lower right, as well as the bolting of the bellows, not particularly fabric if you want to look at it that way, but rubber bellows component in position. Okay. They were resistant to up to 400 degrees Fahrenheit. You want to build within that component the 3-to-1 factor of safety rating for the burst pressure of those components. These happen to range in size from 1.5 inches to about 144 inches at the biggest ones that were built. Different versions of neoprene or rubber expansion joints. Okay, you see one for an air intake component, a gas turbine application, a generator fan. As we talk about, you can utilize them in a variety of applications, working environments, corrosive elements to which they're exposed as well. different configurations. Here you can see, as we talked about, that the fabric lends itself sometimes more to those rectangular configurations. You see the application of the baffle in this application, the utilization of the baffles here. You don't see the internal face of that expansion joint belt material because it's being protected during the flow of abrasive material. In there you see both baffle and another baffle completely insulating, if you will, that expansion joint component. Okay. Just some more application, just giving everybody, more of an overview of how they can be constructed. You can build those attachment points here, all bolted attachment point elements, but they're then built to match the application to which they would be fit, whether it's a stainless steel, highly corrosive environment, whether it's a round flange attachment point, rectangular attachment point, and so on. Some of the capabilities then, as we talked about, you can have expansion joints up to 40 foot long, 20 feet wide in some applications, temperature range up to almost 2,000 degrees Fahrenheit with the inclusion of the insulation pillows, things of that nature. You can develop, for example, a new standard. Here's an example of one that will combine the liner and the flange into one integrated component. So you kind of kill two birds with one stone. And what it does is reduces the amount of welding required, reduces the overall amount of components that are required. You can then utilize if you want to say, a streamlined design by integrating that liner into the flange. You reduce the number of components. You hopefully reduce the amount of production that goes into that component, saving time, hopefully in the end saving money as well. Okay, and so before we close, we'll take a little bit at some of the things to remember during the installation phase, maybe some of the things you want to look at in terms of reviewing existing fabric expansion joints. When you're looking at putting any expansion joint in, but in terms of the fabric expansion joints in particular, you want to do a pre-installation check. You want to confirm the dimensional data of that component, confirm that the flanges that we will be attaching to are in good condition, that they're lined up correctly. Maybe there is supposed to be an offset, as we saw in the one ductwork component. Are they offset in the correct position? Prior to installing the frames, make sure you inspect that component, all those, and then of course make sure that you have all the necessary attachment equipment readily available. We should always use the drawing that has been developed as a guide in looking at the dimensional info. What were the initial set points of that bellows component? Was there initial compression in there? Was there initial extension from the midpoint? Use proper lifting equipment. If there is a liner, again, always make certain that the flow arrow of the liner, which should be reflected on the outside of that bellows whiz, is in the proper flow direction of our media. If not, we'll have a short lifespan. If the ducting is already in place, for example, and you may not be able to move it around for installation, always lift the expansion joint with strap elements, tack it into position, and if there's any welding that has to occur, always remember to protect that fabric belt material from potential damage. Okay, and then when we are reviewing the fabric expansion joints in service, we want to look for, remember, they are different than metallic expansion joints. So you may see a rip or a tear, and that will basically continue on through the entire belt material. You want to observe any damage. Make sure that we haven't exceeded the maximum capacity of deflection. We say, we talked about there's more, relatively speaking, available deflection than we might find in a metallic bellows. But there's always a limit, right? You still can't exceed the overall capacity of that bellows system. So you want to confirm whether or not we are within the travel range, the deflection cycle. Want to look at the seals between our duct work, between our flanges, between our furnace floor and our protrusion. And then you want to ensure that if some of the components can be maintained, maybe the flange is still in good condition. Maybe all those metallic components are still relatively serviceable, and only that fabric belting material has to be replaced. You may have necessity then just to replace the fabric belt component itself, and that's all, and keep the original flanges if they're not exceeded their life cycle. Maybe we just have caused some damage to that belting material. Have the opportunity then, in that case, to replace only the belt. So that basically brings us a close of our review of our overview of fabric expansion joints. Once again, we'll be standing by for a little while if you have any questions. But if something does strike you, say tomorrow, next week, next month, please don't hesitate to contact us at any time. You can reach us at info@pipingtech.com. You can visit our website. Maybe you might see some information that can lead you to an answer. You can see some bulletins on there, some articles, recordings of previous webinars, or you can always contact us, as we've talked about, directly. Any questions, inquiries can be directed to info@pipingtech.com or sales@usbellows.com, and we'll be sure to relay that information to the most appropriate personnel. Once again, I do want to thank everybody for joining us today. We really do appreciate you taking an hour or so out of, I'm sure, your very busy schedules to spend it with us, and we do hope to hear from you soon.